Hello, ma'am. Hello.
Good evening.
Yeah, good evening, ma'am.
Good evening, sir.
Good evening, Ajay. Make me a host, ma'am. How are you, Ajay?
Better, sir.
Mm-hmm. All right, we'll continue. Last class, we learned organic chemistry, some of the methods of preparing haloalkanes. We never learned with the chemical properties. We learned with the preparation of haloalkanes. So many methods we learned, like we learned it from the preparations of alkanes, and second one is from alkenes, third from alcohols, fourth, this is halogen exchange method. We've learned Finkelstein reaction. This is Darcy's process. We learned Finkelstein reaction and Schwarz reaction. This is important. Finkelstein reaction and Schwarz reaction are important. So it is a halogen exchange method, or it is called as halide exchange method. Now, for an example, if you take an alkyl halide like CH3Br, and this is allowed to react with sodium iodide, this Br will be replaced by iodine. Therefore, what we get is we get CH3I and you get NaBr. So replacement or substituting an iodide with respect to another halogen will be called as Finkelstein reaction. And this happens in the presence of acetone as a solvent. Now, similarly, Schwarz reaction. Alkyl fluorides can be prepared by this method. They can be obtained from corresponding chlorides by the action of Hg2F2, mercurous chloride. It's called as mercurous chloride. Now you can see here CH3Cl, Hg2Cl2. This Hg2 and 2Cl gets eliminated as Hg2Cl2, and in place of Cl, F goes. Therefore, you get CH3F. Likewise, the same reaction we can learn. This is also Schwarz reaction. We allow it to react with silver fluoride, AgF. So what happens is this AgCl gets eliminated. In place of Cl, fluorine goes. Therefore, you get CH3F. So methyl fluoride. So alkyl fluorides can be prepared by reacting alkyl bromides or alkyl chlorides with mercurous fluoride or silver fluoride, or they've given here antimony trifluoride. This reaction is called a Schwarz reaction. So these two named reactions, you should remember, Finkelstein reaction and Schwarz reaction. Now, other methods we learned with the reaction of alcohol with Ki, alcohol with halogen, all that we learned. We will learn few of the question based on the preparation part of it, and then we'll continue with the chemical properties. Now, halogen reacts with halogen acids. Halogen acids means what? HCl is a halogen acid, hydrochloric acid. Hydrobromic acid, HBr, is a halogen acid. HI, hydroiodic acid, it's a halogen acid. So acid is nothing but anything which provides H plus ions. This acid, which if it contains a halogen, it will be called as a halogen acid. Halogen acid reacts with alcohols to form alkyl halides. The reaction follows a nucleophilic substitution reaction, a nucleophilic substitution mechanism. What will be the major product of the following reaction? What will be the major product of the following reaction? The reaction is this: CH3, CH, CH3, CH, OH. It's a representation, that's all. You should not ask me why CH3 is on the top and OH is on the bottom. It's a representation. Now, this is an alcohol. This is the reactant what they've given. This alcohol, but it's allowed to react with HCl. Now, this HCl will have H plus and Cl minus. You should remember it will have H plus and Cl minus. So what happens is now the OH minus ions and the Cl minus, what's it, H plus ion gets eliminated as water. When they gets eliminated as water, H2O, the byproduct, what you get is CH3, CCH3, CHCH3, sorry, and CH, you will get a positive charge here, and you will get CH3. Why positive charge? Because OH is eliminated. So the carbon donates both. OH minus is eliminated, not OH. OH minus is eliminated, the bond. So carbon gains what? Positive charge. This is a secondary carbocation. It is a secondary carbocation because this carbon is bonded to two other carbon. Therefore, it is called a secondary carbocation. Now, here this undergoes 1,2 hydride shift. It undergoes 1,2 hydride shift. Now, when I say it undergoes 1,2 hydride shift, what happens is this hydrogen goes here and this positive charge comes to this carbon. So what I have now, CH3, C, CH3, and this carbon has what charge? Positive charge, and you have CH2 and CH3. Are you able to follow? This hydrogen shifts here, hydride, H minus shifts here. Therefore, carbon gains this positive charge, the plus sign shifts here. So now this is a tertiary carbocation. Why it's a tertiary carbocation? This carbon is bonded to three other carbon atoms. Therefore, it's a tertiary carbocation. Now, this tertiary carbocation is more stable than secondary carbocation. So, carbocation stability, tertiary is stabler than secondary is stabler than primary, and primary is stabler than methyl carbocation. This stability of carbocation you should understand. Now, what is left out? We have I minus nucleophile. This I minus, Cl minus, Cl minus will attack the positive sign. Therefore, what we get CH3, CH3. This is the molecule which is major. The major proportion will be this. The minor will be secondary compound, but secondary we're not talking about because the carbocation is unstable. So major is this. They're asking which is the major product formed. The major product formed is this. Hence, the answer for this question is option C. See, if there is no possibility for hydride shift, then tertiary carbocation will not be formed. But here, this H plus or H minus can shift here, and the carbon gains positive charge, forming a tertiary carbocation. Since tertiary carbocation is more stable, the product formed will be option C. Did you follow this?
Yes, sir.
The next question, which of the following compound can yield only one monochlorinated product upon free radical chlorination? Which of the following compound can yield only one monochlorinated product upon free radical chlorination? Now, 2,2 dimethyl propane, 2-methyl propane, 2-methyl butane, and normal butane, small letter n. It is not a capital N, it's a small letter n, normal butane. All right, which of the following compound can yield only one monochlorinated product? Now, propane, 2,2 dimethyl propane. Propane is CH3, single bond C, single bond CH3. Since 2,2 dimethyl, here also you have CH3, here also you have CH3. Now observe this. The substitution can yield monochlorinated. If you chlorinate this, I can show the hydrogen elimination from this carbon, this carbon, this carbon, or this carbon. All the carbon atoms are primary carbon atom. This is a primary carbon atom. This is a primary carbon atom, and all these are primary carbon atom. So I can show the reaction taking place in any place, any of the carbon. One hydrogen will react with chlorine to form HCl in place of that chlorine. Maybe if at all I'm showing this, I can write like this: CH3, CCH3. Here it will be CH2Cl, and it will be CH3. So one of the hydrogen is replaced here by chlorine. Substitution reaction is undergoing. Similarly, anywhere the reaction shown, it's the same. The product is same. So this is a This is the only molecule which can show one monochlorinated product. Monochlorinated product. Hence, the answer for this question is option A. Did you understand, Ajay? Now, if you
Yes,
take
sir.
2-methyl propane, what's that 2-methyl propane? You just see 2-methyl CH3, CCH3, and CH3. Now, this 3 is what? Now, here it will be H. So, this is primary, this is primary, this is primary, but this is tertiary. So, this hydrogen can be replaced, or any one of this hydrogen can be replaced from here. So, you'll get two different products here, chlorinated product. You should be in a position to identify. So, even though this is a quaternary carbon atom, we don't have hydrogen for substitution. Therefore, the product is like. Similarly, with 2-methyl butane and normal butane. The next question. Bromination of methane in the presence of sunlight is nucleophilic substitution, free radical substitution, electrophilic substitution, or nucleophilic substitution. What is this bromination of methane? Now, methane is CH4. We can write methane for our convenience like the CH3 and H. And this is allowed to react with the bromine. It is Br2 in the presence of sunlight. What happens? H and Br gets eliminated as HBr. In place of H, what goes? Br goes. Therefore, you get CH3, Br. This is the product. Methyl bromide is the product. But they're asking, what is the mechanism? Bromination of methane in the presence of sunlight is what type of substitution reaction? So it is, bromine is a homonuclear molecule. All bromine atoms, same atoms. So therefore, what happened? They undergo homolysis. Homolysis means symmetric cleavage. Symmetric cleavage. See, one bromine gains one electron, the other bromine gains the other electron. Therefore, you get bromine free radical. Free radicals are neutral in nature, but highly reactive. So this bromine free radical will attack methane now. CH4, now methane, if I write like this CH4, this will be reacting with bromine free radical. So what happens? H and Br gets eliminated as HBr. In place of this H, this free radical goes. So you get methyl free radical. It goes on like this, the reaction. We will learn the reaction later. Now, this is called as free radical substitution reaction. Why free radical substitution? Free radical mechanism, because in the first step, free radicals are formed due to homolysis. Did you understand this?
Yes, sir.
The next one. Synthesis of alkyl fluoride is best accomplished by, you tell me the answer. Synthesis of alkyl fluoride is best accomplished by. Today also, before the class, we discussed it. Tell me. Synthesis of alkyl fluoride is best accomplished by. What's the name reaction? What is the name reaction? I wrote that reaction. CH3Br are allowed to react with AgF. So what happens? AgBr gets eliminated and you get, in place of bromine, what goes? Fluoride goes. So you get CH3F. What is this name reaction? What is this called as? This is methyl fluoride. What's the name of this reaction?
It's a Schwarz reaction, sir. Option B.
Schwarz reaction. So you should remember, like you can use, instead of AgF, you can use other fluorinating agents like cobalt fluoride also can be used. Mercurous fluoride, HgF2 can be used. You can use arsenic fluoride can be used, and antimony fluoride also can be used. All these are called as fluorinating agent. Not only AgF, any of these can be used. And the name of this reaction is Schwarz reaction. The next question. All right. Which of the following alcohol will yield the corresponding alkyl chloride on reaction with concentrated hydrochloric acid at room temperature? Which of the following alcohols will yield the corresponding alkyl chloride with concentrated HCl. Think and tell me the answer. Let's see. Now identify something. Now, if I have the first option, this is a primary alcohol because this carbon is a primary carbon atom because it's bonded to one more carbon atom. Now, if you write like this, the second one, if you see CH3, CH2, CH, CH3, and OH, what type of carbon atom is this? Secondary carbon atom, because this carbon is bonded to two other carbon atoms. Now, if you talk about this, option C, CH3, CH2, CH, CH3, and CH2OH. Now, this is a tertiary carbon atom. Tertiary carbon atom, because this carbon is bonded to three carbon atoms. Now, if I'm talking with respect to the fourth one, I'll take like this CH3, CH2, CCH3, CH3, and OH. This is tertiary carbon atom, and this is tertiary alcohol. See, this is a tertiary carbon atom, no doubt, but OH is bonded to what carbon atom here? Primary carbon atom. OH is bonded to primary carbon atom. In the previous questions, we learned that tertiary carbon atoms are more reactive. Now, tertiary carbon atoms are more reactive, meaning this alcohol, tertiary alcohol, will be more reactive towards hydrogen halide. H and OH gets eliminated. In place of HCl goes. Therefore, what's the product? Major product, you'll get a CH3, CH2C, CH3, CH3, and you will get what? Cl, tertiary alkyl chlorides. All right. Therefore, the answer for this question will be option D. You should remember tertiary alcohols are most reactive. They react reactive, therefore react with HCl at room temperature to form the major product. Followed this, Ajay?
Yes, sir.
The next one, which reagent will you use for the following reaction? Which reagent will be used for the following reaction? Tell me, chlorine, UV light, NaCl, sulfuric acid, chlorine gas in dark, chlorine gas in the presence of iron in dark. It's a simple question possible. Now, substitution reaction. It's a substitution reaction. You can see here also you get chlorides, here also you get chlorides. For substitution reaction, we will use chlorine gas in the presence of sunlight. So the answer will be option A. Direct chlorination of alkanes takes place in the presence of sunlight. Direct chlorination of alkanes takes place in the presence of sunlight. The presence of sunlight, specifically UV light. Hence, the answer for this question is option A. Now, you tell me this reaction. CH2 double bond CH single bond CH3 plus HBr, giving you CH3, CHBr, CH3 is an example for nucleophilic addition reaction, free radical reaction, electrophilic addition reaction, or its electrophilic substitution reaction. Firstly, you should understand that this molecule contains a double bond. When it contains a double bond, it has to undergo addition reaction. It cannot undergo substitution reaction. So unsaturated molecules will always undergo addition reaction, whether it's a double bond or a triple bond. You can clearly observe that here bromine Br minus is attacking and here H plus is attacking. All right. So what kind of reaction it is? Now HBr, this HBr will undergo heterolytic fission. What do you mean by heterolytic fission? Both the electrons are gained by bromine here because bromine being electronegative, Br minus and H plus. Now this H plus will be called as an electrophile and Br minus will be called as nucleophile. Electron-rich groups are called as nucleophile. Negatively charged ions are called as nucleophile, and H plus ions are called as electrophile. Electron-deficient groups are called as electrophile. So this addition of hydrogen bromide to propene follows Markovnikov's rule. Markovnikov's rule. So the mechanism which follows here is electrophilic addition reaction. So it's an electrophilic addition reaction because electrophile is formed. First electrophile only will attack, only then nucleophile. So it is called as electrophilic addition reaction. Option C. Next question. Which of the following reaction follows Markovnikov's rule? Which of the following reaction follows Markovnikov's rule? You tell me, Ajay. Option A, B, C, D. Now, if you take a molecule, if you take a molecule like this, ethene, CH2 double bond CH2, if I allow this to react with hydrogen bromide, assume hydrogen attacks this and bromine attacks this. So you get CH3 single bond CH2 and Br. Now, if I write, the yes, tell me.
Sir, is it option C, sir?
It is option C. If I write like this, Br and H attacking here, so I get CH2 Br and also CH3. So the products are same. Symmetric alkanes will give only one product. Remember, so Markovnikov's rule will not be applicable for a symmetric alkene. All right. And for Markovnikov's rule, we need to have hydrogen halide. It is not halogens. So these two are ruled out. So if you write this CH3, C3H6, what is the C3H6? CH3, CH double bond CH2. This is C3H6. It is propene. It is an unsymmetrical alkene. What do you mean by unsymmetrical alkene? This alkene cannot be divided into two equal halves. To this unsymmetrical alkene, if hydrogen bromide is added, the negative part of the added molecule gets bonded to the carbon containing less number of hydrogen. Therefore, you get CH3, CHBr, and single bond CH3. So this is the molecule which will follow Markovnikov's rule. Here it is symmetric, since Markovnikov's rule will not follow. So unsymmetrical alkenes only will follow Markovnikov's rule. Hence, the answer for this question is option C. All right, good. The next question. In the hydrocarbon, CH3, CH, what's that? They've given CH3, CH double bond, CH, single bond CH2, single bond C, triple bond CH. The states of hybridization of carbon 1, carbon 3, and carbon 5 are. So tell me, you have a double bond here as well as you have a triple bond. So from which direction you will start counting it? From my left to right or right to left? Which way I'll count? Which will be given the preference? Alkynes are given, triple bond is given preference. So therefore this is ruled out. So I have to count it from my right to left. When I count it from my right to left, 1, 2, 3, 4, 5, and 6. They're asking first carbon atom. First carbon atom, we have a triple bond. Since we have a triple bond, this will be sp hybridized. Third carbon atom, we have a single bond. So therefore it will be sp2 hybridized. And the fifth carbon atom, it has a double bond. So it will be, this is sp3 hybridized, sorry. This is sp3 and here it will be sp2. So therefore, the answer for this question will be option B, sp3 and what? sp2. Did you understand? Carbon to carbon triple bond, it is sp. Carbon to carbon double bond, it is sp2. And carbon to carbon single bond, it is sp3. Followed?
Yes, sir.
Next question. Which amongst the following is most stable carbocation? Which amongst the following is most stable carbocation? Tell me, this one is what? If I write like this, CH3, see the way they give and don't think it is a complex. You should be in a position to identify. What type of carbocation is this? It is a secondary carbocation. Why it's a secondary carbocation? This carbon is bonded to two more carbon, secondary carbocation. If you talk about B is CH3, C plus, you have CH3 and CH3. You need to know how to write the structures. This is tertiary carbocation. And this is methyl carbocation, CH3 plus. And this is also ethyl carbocation. So this is methyl carbocation, this is primary carbocation. Which among the following is more stable? Which among the following is more stable? You should know that tertiary carbocation is more stable than secondary, stable than primary, and primary is more stable than methyl carbocation. So since tertiary is more stable, the answer for this question, the order of stability of carbocations, tertiary is more stable than secondary. Remember, hence the answer for this question is option B. Followed?
Yes, sir.
Yeah. Now, physical properties of alkyl halides. We have to learn chemical properties as well as the physical properties. Let us understand a few of the chemical properties and physical properties now. We learned the preparation and also we learned some of the MCQs based on that. Now we are going to learn the physical properties. The physical properties. Methyl fluoride, methyl chloride, methyl bromide, and ethyl chloride are gases at room temperature. The alkyl halides up to C18, carbon 18, are colorless liquids, while higher members are colorless solids. Now, few gases we have: methyl fluoride, methyl chloride, methyl bromide, and ethyl chloride. They're all gases at room temperature. But all the other alkyl halide up to carbon 18, they are colorless liquids, while higher members are colorless solids. It's a physical property. Nobody will ask you any question based on this. Now, alkyl halides are insoluble in water, but soluble in organic solvents. Why? They are insoluble. They do not form hydrogen bonds with water. Since they do not form hydrogen bonds with water, they are insoluble in water. Even though alkyl halides are polar molecule. Now, just if you take CH3Br, Br is partial negative and carbon is partial positive. It's a polar molecule, polar molecule. Water is also polar, like dissolves like. That's what we understand. But here, this alkyl halides will not be in a position to dissolve in water because they do not form hydrogen bonds. Now, the next is they burn on copper wire with green-edged flame. It's called as Beilstein's test. Presence of halogen is determined by Beilstein's test. What we do is a copper wire is dipped into an organic liquid and it's subjected to the non-luminous flame, blue color flame in the Bunsen burner. So you will get a green edged flame. So if this is a flame, you will get green edged flame like this. You will get the green edged. This edge will be what? Greenish. The presence of this halogen is determined by what? The flame with the green edge. All right. So that test is called as Beilstein test. This is the identification test for halogens. Next, alkyl bromides and alkyl iodides are heavier than water. Alkyl chlorides and alkyl fluorides are lighter than water. Alkyl bromides and alkyl iodides, bromine and iodine, they have atomic mass larger. Therefore, alkyl bromides and alkyl iodides are heavier than water. Now, alkyl halides becomes violet or brown in color on exposure as they decompose in light. Alkyl iodides becomes violet in color on exposure as they decompose in light. See, this is alkyl iodide. So for an example, if I take CH3I, this alkyl iodide will decompose to form CH3 ethane and gives you what? Iodine. This iodine which is formed becomes what? Violet, or it appears to be brown in color. Now, for a given alkyl group, the boiling points of alkyl halides are of the order. Boiling points of the alkyl groups of the order for a given alkyl group, meaning I am comparing only alkyl iodides, that's methyl iodide with methyl bromide, with methyl chloride, and with what? Methyl fluoride. See, all the alkyl groups are same here. Only the halogen is different. For these kind of molecules, alkyl iodides will have higher boiling point compared to alkyl bromides, alkyl chlorides, or alkyl fluorides. For a given halogen, the boiling point of alkyl halides increase with increase in size of the alkyl group. Meaning, for an example, if I take C2H5Br and I have CH3Br, both are alkyl halides. Now you can see this alkyl group is bigger compared to this. Since the alkyl group is bigger, now halogens are same here, both contains bromine, but here alkyl groups are what? Different. Here, the heavier alkyl group, as the molecular mass increases, the boiling point and melting point increases. You should remember. So, since the heavier alkyl group, the bigger alkyl group, the boiling point and melting point will be greater of this ethyl bromide compared to methyl bromide. Are you following? Ajay, are you following?
Yes, sir.
Yeah. Alkyl halides are in general toxic compounds and bring unconsciousness when inhaled in large quantity. So alkyl halides are generally toxic compounds and brings unconsciousness when inhaled in large quantity. All right, some of the questions based on the physical properties, and then we're going to learn with the chemical properties. A lot of reactions we'll be learning in this chapter. Which of the following molecules has highest dipole moment? Which of the following molecule has highest dipole moment? Chloromethane, dichloromethane, chloroform, and carbon tetrachloride. Which of the following will have highest dipole moment? So dipole moment is defined as, what is dipole moment defined as? Dipole moment is defined as charge into distance. Dipole moment we represent by a letter mu. Charge into distance is called as dipole moment. Charge into distance. Now, which of the following will have highest dipole moment? Chloromethane will be having higher dipole moment than dichloromethane, and that will have higher dipole moment than trichloromethane, and trichloromethane will have dipole moment greater than carbon tetrachloride. See, in all these, carbon is undergoing sp3 hybridization. The shape of the molecules will be tetrahedral. Now, if you observe this chloromethane, since chlorine is more electronegative, the charge difference will be more here and hydrogen. But when we take carbon tetrachloride here, now all the four corners of the tetrahedron you have chlorine. The dipole moment will be cancelled. This will get cancelled here and this will get cancelled here. So dipole moment will be almost zero for carbon tetrachloride, CCl4. But it is not so for that. Charge into distance, right? Therefore, the dipole moment of chloromethane will be greater than all other compounds. Hence, the highest will be option A, CH3Cl. Next, which of the following compounds has the highest boiling point? Which of the following compounds has the highest boiling point? Now, firstly, you should remember 2-3 points you should remember with respect to the boiling point. Now, all the compounds contain same halogens. All the compounds contain same halogen. Here it's chlorine. For the same halogen, boiling point of alkyl halides decreases as size of alkyl group decreases. Size of alkyl group decreases. Meaning, larger the alkyl group and the boiling point will be the boiling point will be greater for same halogens. Now, for isomeric alkyl halides, boiling point decreases as branching increases. Now, for isomeric alkyl halides, for isomeric alkyl halides, boiling point decreases as branching increases. Now, isomers, compounds having same molecular formula, same structural formula, but differ in the positions of the substituent. That will be called as position isomers. So as the branch increases, you should remember the boiling point decreases. Now, none of them is what an isomer here. All are different molecules. All are different molecules. So if that is the case, we understand for isomeric alkyl, boiling point decreases with increase in branching. Here, the molecular mass of this will be lesser compared to this, and this. So the order will be CH3, CH2, CH2, Cl will have larger boiling point. No, another CH2, this one, CH2Cl, the second option. This will be first, highest boiling point first. And this will be greater than CH2, CH2, CH2Cl. See, there is no branching here. But the third one, what I'm writing, if you observe, here we have CH3. Whatever is written in the brackets are a branch. Remember that. So as branching increases, what happens? The boiling point has to decrease. And if you observe the fourth option, it is highly branched. 2 branches you have. There's at least only 1 branch. If you count this as a long chain, it has 2 branches. Therefore, what happens is the boiling point decreases as branching increases. Now, which of the following compounds has highest boiling point here? It will be option B. The option B has highest boiling point. 2 points I told you. One is for same halogen, the boiling point decreases with decrease in size of alkyl group. Or I can put it like this: as the alkyl group increases, the size, the boiling point increases. It's all the same. The second point is for isomeric alkyl halides, boiling point will decrease as the branching increases, side chain increases, branches increases. The third question is, which of the following is not correct order of boiling point of alkyl or aryl group? Which of the following is not correct order of boiling point of alkyl or aryl halide? We are not talking about the aryl halide. Aryl halides means ring compounds here, a benzene ring compounds. So here we are not, none of them is an aryl halide. All are alkyl halides. Which of the following is not the correct order of the boiling point? Now, in case of the option C, CH3, CH3, 3 branches. And here, if you observe, CH3 twice. So I can write as CH, CH2, CH2, and maybe I can write it as CH2Cl. So if I can, this is CH3, sorry. This is also CH3. 1, 2, 3, if I take, there is only 1 branch here. Here, if I take 1, 2, 3, there's 2 branches here. So as the branching increases, what happens? The boiling point has to decrease. But what they have said here, the boiling point increases, they say. It is a wrong option. So therefore, the answer for this question is option C. Followed?
Yes, sir. Followed, sir.
Alkyl halides are immiscible in water, though they are polar. I told you the answer already. Though they are polar, alkyl halides are polar molecules. Water is also a polar, but they are not soluble. Why they are not immiscible? Because they cannot form what? Hydrogen bonds with water. Since alkyl halides cannot form hydrogen bonds with water, these alkyl halides are not soluble in water. Arrange the following compounds in the decreasing order of their boiling point. The decreasing order of their boiling point. So as the branch increases, the boiling point has to decrease. For this, no branch. Here you can see 2 branch, and here it is 1 branch. So they're asking you to arrange the following in the decreasing order. So decreasing order should be highest to the lowest. So option, this one is greater than 3, and it will be greater than 2. Why? Because in the first case, no branch. In the second case, you have CH3, C, CH3, CH3, and Br. 2 branches here, side chains. But in the third, you have only 1 branch, CH3 and Br. So branching is less here. Therefore, the boiling point will be greater than this. Answer is option A. Did you follow this question, what I was talking about?
Yes, sir.
The magnitude of van der Waals force goes on decreasing with branch. So as the branch increases, what happens is van der Waals force of attraction decreases. Therefore, the boiling point also will decrease. Now, we are going to learn with some of the chemical properties of alkyl halides. Chemical properties. The alkyl halides are highly reactive. The order of the reactivity is iodides are more reactive compared to bromides. Bromides are more reactive compared to chlorides based on the nature of halogen atoms. Meaning, if I have an alkyl bromide like methyl bromide, a methyl iodide, a methyl bromide, and methyl chloride. Amongst this, the order of reactivity will be iodides. Methyl iodide will be more reactive than bromides and chlorides because iodine is a larger atom. So therefore, the bond strength will be lesser. Iodine bond strength will be lesser. Therefore, it's reactive. The second is based the type of halogen atoms. Tertiary is greater than secondary. Secondary is greater than primary. Amongst the primary alkyl halide, the order is. See, among the primary alkyl halides, the order is all are primary alkyl halides. Now, this is a smaller molecule. The high reactivity of alkyl halides can be explained in terms of nature of carbon-hydrogen bonds, which is highly polarized covalent bond due to large difference in electronegativities of carbon and halogen atom. The halogen is far more electronegative than carbon and tend to pull the electron away from carbon. That is, halogen acquires a small negative charge and carbon acquires a positive charge. It's explained here. It's carbon and halogen. Since halogen is more electronegative, it pulls the electron pair towards halogen. So halogen gains negative charge and carbon gains positive charge. But in case of the molecule here, if I write CH3, CH2, and a halogen like this, this also electron pair will be pulled towards a halogen. Halogen gains negative charge and carbon gains positive charge. But the polarity here will be what? Lesser, because this is an electron donating group. In methyl group, there is no substitute. There is no electron donating group. Therefore, this is more reactive. Methyl halides are more reactive than ethyl propyl halides, etc. The polarity is responsible for the reactions. This polarity, what is this polarity? So the polarity which is developed between carbon and halogen. Carbon and halogen. Halogen is electronegative. The bonded pair of electron will be moving towards halogen. Halogen gains negative charge and carbon gains positive charge. This polarity developed in a molecule is responsible for reactions. When we say it's responsible for reaction, it undergoes 2 different types of reactions. One is a nucleophilic substitution reaction. The other one is electrophilic elimination reactions. So alkyl halides will undergo nucleophilic substitution reaction, and it also undergoes elimination reactions. The first one is nucleophilic substitution reaction. It is also called a substitution nucleophilic reaction. Therefore, it's called as SN reactions. S stands for substitution, N stands for nucleophile. The carbon positive, carbocation, see carbon delta plus, carbon gains positive, is susceptible to attack by the nucleophiles. Nucleophiles are electron-rich group, and carbocations are electron-deficient group. In case of nucleophilic substitution reaction, the nucleophile will tend to attack the carbocation. What is this carbocation? Carbon having positive charge will be called as carbocation. Now, if you observe, we're going to learn the reactions in detail. Rx is the general representation of alkyl halide. This alkyl halide, the halogen gets eliminated. It's a slow process forming a carbocation. This carbocation will be attacked by nucleophile, which is a fast reaction, to give RNU. It is called as SN1 mechanism. It's happening in 2 steps. The first step is the formation of carbocation, which is a slow step, and next is attack of nucleophile. That's a fast step. So SN1, what is this SN1? S stands for substitution, N stands for nucleophilic, 1 stands for unimolecular. Unimolecular. We will learn this mechanism in detail now. Now, similarly, if you see Rx, it's an alkyl halide. If the nucleophile is attacking the alkyl group from the opposite side, from the rear side, it's a slow process and it undergoes a transition state. Once the nucleophile is completely attacking the R group, then the R and X bond will break. And this reaction is called as SN2 mechanism. SN2 stands. So the reaction which is called as what? Substitution nucleophilic bimolecular reaction. Now, examples for SN1 mechanism. Some of the examples we will learn, mechanism we will learn possibly tomorrow. Now, alkyl halide is Rx. We generally represent an alkyl halide by Rx. So CH3Br, alkyl bromide. This alkyl bromide, when we allow it to react with silver hydroxide, excuse me, the silver hydroxide will give you Ag plus and OH minus. This OH minus will be called as nucleophile. So what happens is Ag and Br gets eliminated as AgBr. In place of Br, what goes? OH. Therefore, the product what we get is CH3 OH. You get an alcohol. So it's called a nucleophilic substitution reaction. Because OH is what? A nucleophile, OH minus, electron rich group. Similarly, the same reaction if you perform it with KOH, methyl bromide, when it's allowed to react with KOH, Br and K gets eliminated as KBr. In place of Br, what goes? OH goes. Therefore, you get CH3OH. So when alkyl halides are allowed to react with the base, like silver hydroxide or potassium hydroxide, what happens is nucleophilic substitution reaction takes place, forming alcohols. So this is the first reaction. SN1 mechanism, substitution, SN1 or SN2, the products are always alcohols. Now, with the help of this reaction, an alkene can be converted into an alcohol. Alkene is first treated with HBr to form alkyl bromide, and then hydrolysis is done. So, alkene is CH2 double bond CH2. When this is allowed to react with HBr, H attacks this carbon, assume, and Br attacks this carbon. So, what happens? A pi bond will break. So, you'll get CH3, CH2Br, CH3, and CH2Br. This is ethyl bromide. When this is allowed to react with AgOH, silver hydroxide, it's called as hydrolysis. Ag and Br gets eliminated as AgBr. In place of Br, what goes? OH. Therefore, you get ethyl alcohol. So one of the method of preparing alcohol is by reacting an alkyl halide with a base like sodium hydroxide or silver hydroxide. So hydrolysis will take place, forming alcohols. Next one is reaction with alcohol oxide or dry silver oxide. Reaction of alkyl halides. This topic is alkyl halide, remember. So reaction of alkyl halides with alcohol oxide or dry silver oxide. Now, alcohol oxide, sodium alcohol oxide, silver, whatever it is. Now, if you take a molecule like the CH3Br, this is alkyl halide. When this is allowed to react with ethyl alcohol oxide, what do you mean by ethyl alcohol? C2H5OH is ethanol. In place of H, sodium is be replaced. So therefore, it will be called as sodium ethoxide. So the name of this molecule will be called as sodium ethoxide. In general, it's called a sodium alkoxide. What happens? Ag and Br gets eliminated as AgBr. So what else is left out? I have CH3, I have O, and I have C2H5. This is nothing but an ether. So from alkyl halide, we can prepare ethers also by the reaction with alkoxides. Similarly, an alkyl halide, if you take CH3Br, CH3Br, when it is allowed to react with dry silver oxide, you should have dry silver oxide. If you use moist silver oxide, hydrolysis will take place. To avoid that, we need to use what? Dry silver oxide, Ag2O. Now you can see this 2Ag and Br gets eliminated as 2AgBr. What else is left out? I have CH3, single bond O, and you have another CH3. It is also a method of preparing ether. Organic compounds having O as a functional group is called as ether. Did you follow this?
Yes, sir.
One more reaction and then we'll stop. This is reaction with sodium or potassium hydrogen sulfide. Sodium or potassium hydrogen sulfide. So Rx is an alkyl halide. So you can write CH3Br. This is allowed to react with sodium hydrogen sulfide. NaSH. So what happens? Na and Br gets eliminated as NaBr. And in place of Br, SH goes. Therefore, you get CH3SH. So this reaction is not there in the syllabus, but remember, it is again a nucleophilic substitution reaction. So we will learn the other set of reactions possibly tomorrow. We will stop the class for now. Madam? Ma'am, I'll stop the class. Ma'am?
Yes, sir. Thank you, sir.
Bye, ma'am.